Okay, good afternoon, everyone. Technical session 2 is starting now. Very glad to see all the networking happening outside, but we really have to start this session. Otherwise, we will run late. So again, hello, everyone. This is Technical Session 2. My name is Cheryl Shane Hermosa from APNIC, and I will be the session moderator. So we have 3 amazing speakers today joining us in person and also remotely. Each speaker will have about 20 to 25 minutes to speak, and then we will entertain questions after that. If you have questions over Zoom, please type it in. For those who are in the room, there are microphones that are available for you to ask those questions. So with that, without any further ado, let me introduce our first speaker. Here is Christoph Dietzel, the head of product and research department at DKIX, to talk about IXP Scrubber.
Thank you so much. So to lift this up. I got 2 now, so both work. Let's see. Okay, thanks for attending my talk. I'm really excited to talk today about IXP scrubbing, learning from blackholing traffic for machine learning driven DDoS detection at scale. So that is a project actually run by my team and wonderful colleagues of the university in Cottbus, and particularly we also had a paper submitted or actually accepted at SIGCOMM 2 months or like 1 month ago, and the wonderful work specifically done by the first author Matthias Wichtelhuber will be the content for this presentation today. Okay, none works. Next slide. Okay, so the topic is not really new to you, right? DDoS attacks, they are all over the place, and actually there are millions of ongoing attacks each and every day, and there are globally growing about 14% by year. And currently the publicly known one, there might be also ones that are not publicly known and not in the literature, is a peak of 3.5 terabits per second, an average of 1 gigabit per second. It is a frequent problem to network operators like us because they saturate our links, right? They cause trouble and they actually just cost money. So actually, therefore, we as an internet exchange operator at DKIX thought we need to come up with a solution as depicted in this figure that we can actually drop the packets halfway, like at the IXP already, right? Not at your edge routers, but rather even a step before. So we could delegate it by 1 hop and maybe even stop 1 or more AS hops in 55% of the attacks, which we have shown in a previous study. And that removes stress from your infrastructure and makes your life better. And we actually, in the way how we implement it, don't really need to add anything new but a bit software and a few servers. So the question I'm asking now is basically, how can we build such a DDoS mitigation technique, and specifically an automated detection algorithm, so that we can really have it to fulfill our operational requirements? And therefore, obvious question is, what are the operational requirements? These requirements are, okay, we need the low cost, right? We don't want to really buy expensive boxes or other pre-products from the huge vendors that actually offer DDoS mitigation services. So we don't really want to invest a lot into maintenance. So we don't want to interfere manually. We don't want to tune algorithms or dig into log files each and every day. So once it is developed and implemented, it should just run by itself. And it should also be member driven, which means we just provide the tools and the members would decide whether they use it to the full extent or just partially in semi-automated way, or maybe even in a fully automated way. So we leave the power to our members. And it also needs to be controllable. So it means we don't want to have a lot of damage from false positives, and we need to understand the performance. And that's increasingly an issue if people apply machine learning algorithms where they actually don't really understand what's going on, and they're just looking at outcomes and crossing fingers that everything works. So here is a nice toy example. It is the IXP in the center, and you have 4 networks connected to this IXP. And one member A is sending DDoS traffic, and the DDoS traffic goes mainly to the ASD. So there's a very common tool. It exists for ISPs as much as IXPs, and it's called black holing. It's a standardized procedure where we can drop traffic by IP prefix, and IP prefix can also be a most specific /32 in this scenario. So the member actually tells us, hey, drop please the traffic towards this IP address, and then it will be discarded actually at the IXP already. So what we want to do and what our contribution is we want to generate a training set out of the huge amounts of data that we actually see coming from this black holing service, because the advantage is many members at DKIX are using this black holing service, and but not all of them. So we have the opportunity to really have a very diverse data set here. Then we want to perform some self-learning, and we want to have locally explainable IXP scrubbing machine learning models. So we want to generate a model that we ideally can even transfer to other locations, but that it's in the first instance locally. And this model we want to understand and want to evaluate the model drift. So each model you generate at day 1 might not be valid 30 days later and does not really work for detecting attacks anymore. And obviously, since we operate multiple IXPs, we want to also see how easy can we actually move a model that we've trained at one IXP to another IXP. How well does it work, or does it not work at all? So therefore, we crowdsource our DDoS labeling with black holing. And in the scenario which we have here is, again, the attack scenario. And we see that the control flow, which is the dashed line, where the BGP or the IP addresses or prefixes are distributed or marked traffic to be discarded, which goes towards these prefixes. And we see that the member ASB, the traffic actually is dropped. However, this does not work for all the networks, because roughly 50% of the networks actually don't really accept the announced prefixes, so that we still see that the traffic is still coming through, or they actually not relying on a black holing mechanism at all. And now what we want to do, we want to use this generated data set from this, where we can clearly see this is a flow, and we associate the flow with a feature, whether the traffic is wanted or unwanted, like at the end of the day. And our training size set is actually only limited by the size of the flow. So actually, we can really generate super huge data sets. It's only a matter of the time we're actually capturing the data, right? So if we take a week longer, then we can just capture 1 week longer data set. So we don't want to be limited by anything else. So an issue we have here is that black holing traffic, or traffic that got black holed, traffic that is potentially DDoS traffic and got discarded, only constitutes for about 1% of the traffic in the raw format. So 99% of the traffic is actually non-black holing traffic, so benign traffic, which is supposed to be there. However, for the algorithms, the machine learning or the classification algorithms we want to use later, actually we need a balanced data set. And therefore, we had the issue, okay, we need to balance it here, and want to get rid of the underrepresented black holing rules. And therefore, we actually have to reduce the data set by 99%, right, to be able to really balance it 50-50. Just for clarification, actually, we operate with 2 different kinds of data sets. So one is the aforementioned ML training data set, where we rely on black hole data and record the features of these flows. We have really billions of flows and 3 to 24 months worth data here. mostly coming from EU and US locations. And after the balancing, we only end up with 202 million flow records. And this data set we want to use for the machine learning pipeline design and for the training performance evaluation. However, we also need another data set for evaluation and validation at the end. And therefore, we ran self-attacks to our infrastructure and collected this data set as a sort of ground truth data set, which we can later use with a very, very small number of flows, but we have the evidence that all these flows are actually really attack traffic. So now we have two nice data sets, as you can see here, the two plots, and we have the self-attack set and the machine learning set. So at first glance, we actually see they look more or less very similar. So they have comparable traffic mixes, right? So it's all the well-known attack protocols that we see in here, and the distribution is not so different. However, there's one thing that strikes the eye, and that is actually the challenge as we move forward, that our black holing data is impure. So only 15% of possible, 15% of this data set, of the machine learning training data set, could also be benign traffic. So it looks odd at the first glance. So therefore, we run a machine learning model classification process to construct the model. And what we actually do, and what you can see on the left-hand side of the slide, is we use DDoS or the data set where we have the DDoS and the benign flows and tag them accordingly. So we tag the signal flows, and then we want to see later how likely are they part of a DDoS attack or not. And this solves our impurity problem for the black holing data set. Then again, we also do a macroscopic machine learning model, which actually classifies the targets into the attacks, essentially attack or not attacked. And now I go into detail for each of the two steps, what we're doing to achieve a good data set and then a good ML performance. So the macroscopic level is the flow tagging, so tag each flow. And actually we use ARM for it, associated rule mining, and that you probably know that stuff from Amazon. So, hey, customer buying milk also bought bread. So you just try to correlate two different events. And in the example, we have here an attack, or we want to do now the opposite. We have a flow, and we're asking the question, if you look at the parameters of this flow, how likely is it that this was a DDoS attack? And then we actually tag this flow. What we also did, and what was really crucial, because I said earlier, we don't want to rely only on such classifications and later on the ML procedures. We actually really want to have some experts, some humans in the loop for the real validation. And therefore, we actually constructed such a user interface with all the flows in, where a user could go through, and we asked 15 different experts to really go through and validate if it makes sense that we see an attack here as a further step to improve the performance. So on the macroscopic level, again, we wanted to identify the target. So was this target a target of an attack? And we wanted to do it independent of the location. Yeah, as I said, so independent of the IXP location. And therefore, we used the weight of evidence method, and it's for encoding of categories. And basically, where you might know, probably not know, but the credit card scoring systems are actually using the very same mechanism to tell if someone will get a credit or not. And we use this one because it is very nice that we can, at one step, really assign the weights of evidence given different features we are seeing, and later on only see this value, and based on this one we can make the decision. So here you see the examples: a positive risk score for reflector IP addresses that are well-known reflectors, NTP, SSDP, and we see a negative risk score, so very unlikely that it is part of a black hole. is HTTP, for instance. So, and we actually split the step, so that makes it easier to make this classifier transferable. And first, we do the weight of evidence encoding, and then we generate and then we run the classifier. And by separating these two steps, we are much more flexible later on for doing it at different locations. So let me quickly look at the general performance. So we also evaluated 5 optimized machine learning classifiers on all data sets. And the best performance had the XGBoost algorithms with a F1 score of 0.98, or actually even above. So really, really good performance. And if we look at the retaining, one issue, of course, with detection of attacks is over time, the patterns might change and the model tends to drift, so that the detection is not as accurate as before, or that there is a higher chance of false positives. And therefore, we compare it if we just have a sliding window that is day, week, or month. And we actually see that the median here hardly affects, or that the window size hardly affects the median. However, we see that we generated a lot more outliers. And actually, with respect to false positives, we don't want to generate outliers. So we saw that the performance remained stable, but that it is better to have a slightly wider window. So then we actually asked the question, okay, but how transferable is it? And we therefore played around with data coming from 5 different locations. And when we first ran it and transferred the weight of evidence encoding and the classifier, like both together, which I said the 2 different steps that you can separate from each other, we just transferred it together. We actually see the bright color is not so successful, so a rather bad performance. The darker it gets, the more bluish, the better. And we actually see only when we have at the y-axis the IXPs used for the training, and on the x-axis the IXPs used for the evaluation, we clearly see that only the diagonal squares are actually darker color, and some others, which tells us basically transferring does not work very well, right? It's only if you train it, at it, and then you do the evaluation at it, you get the good scores. And therefore, we actually use the trick that we sort of introduced earlier, that we separate the classifier from the weight of evidence encoding. And the weight of evidence encoding remains local, coming from the local data source, and the classifier is the global one. And then we see that we actually have, in general, a very good performance. And it does not really matter where you train the model, and where you do the encoding, and then later where you do the classifying. I mean, there are also some outliers, but the overall picture is that it's very easy to transfer. So by achieving this, actually, we really found a solution that has a low cost. It has low maintenance. We figured with the model drift, that is not a critical issue. We feel confident to push this further. I mean, it's not in operation yet, but really the results we have here now are so tempting that we will pursue this road and keep going. And also member-driven, they can decide whether they want this in the first place, which kind of filters they want, and the degree of automation they want. And also, yeah, it's a very controllable, because we have really low false positive rates. This was really the very short summary of the entire process and the different steps. And I know in some details it's a bit more complicated, or you might be a bit more curious to understand the details. And therefore, we have this full paper here where you can find a lot of plots and also a lot of descriptions and yeah, many, many more details. So thank you so much. That's from my side. And yeah, happy to take questions if there are.
Thank you, Christoph. Okay, questions?
Hello, hi, wonderful presentation. My name is Vidya Sagar. I'm a cybersecurity researcher from CERT India. So my question is about the feature selection you have used in the model training. So can you detail us about the features you have used in IPv4 and v6 packet?
Yeah.
What features you have used for the model selection?
Yes, so actually it's super simple. It's just metadata, obviously, and it's just source, destination IP, ports, protocol, packet size, so transferred bytes and packets per flow.
Okay. And any layer 7 metadata you have used for feature selection?
Again, any
layer 7 TCP IP layer 7 application?
No, nothing.
No metadata.
So IXP is layer 2, and we didn't touch and look at anything that's up
layer
to
3 and 4 only. Here, in layer 3, IP could be misleading one because like threat actors use one set of IPs at one point of time.
Yeah.
See, if we provide that as a feature for our hyperparameter tuning or a calculation, so that kind of misleads, right? Because that same IP could be benign at one point of time, malicious at another point of time. How you have solved that issue?
Yeah, indeed. So that's true. But the point is here with our weight of evidence, we actually so the likelihood over time for an IP, like you just look at this window, and the likelihood actually increase if it is seen in more events where we actually saw the attacks, right? So, and if it over time decreases again or is completely gone, actually we wouldn't assign a negative weight of evidence.
Okay, there will be always some model drift.
Yeah, of course. That's why we keep like recalculating basically with a sliding window, but actually all the time keep recalculating and moving the window.
Okay, thank you.
Thank you.
Go for it. Yep. Eduardo, I'm a community trainer, APNIC. My question is, first of all, it's a really good research. Good work.
Thank you.
I'm just wondering regarding the methods that you use. Do you consider rate limiting as part of it?
Yes, so we have upper and lower boundaries for it, but actually, yeah, what I mean, that was like the super short version here now. Actually, we looked at a lot of different approaches to classify and later also to run it, which I didn't mention here. So there was a whole lot of try and error before involved till we ended up with the algorithms we eventually used.
Oh, nice. The other thing is, since you're using this, you have developed this method. Are you looking to build a database for others out there that are doing similar work? Because what you're looking for is patterns, right?
Yeah,
in your machine learning.
It's a really good question. I love it. The thing is, we at the RIPE meeting, we actually shared a list of features that we actually found. So we put it on GitHub back then. We had some discussions whether it should stay, but we believe, yeah, in general you can share it because it's not really. So we have, of course, no IP or anything like that, but just the results of the classifiers, and that could be really useful to any other network operators as well. Yeah, indeed.
Yeah, thanks.
Barry Green from Akamai. On the data sharing, two sources that you can build a relationship with. One is the Ddos Information Sharing System, which is based out of the United States at Cable Labs. That's actually a functional system where you got a lot of service providers sharing similar sort of data sets from attack data. And the other one is Shadow Server, which is also doing those data sets. Now, the reason why I plug it into those is that the model and the drift, one of the things to kind of be mindful of is there's two variables going on right now in activity. So when you did these initial work with it, if you probably did it today, you're probably going to see the variance of the model shift, because you have on one side, you have mitigating forces of the industry pushing back against DDoS miscreants, which is forcing them to not do so much on reflector base, but to do on more proxy.
Yeah.
And the attack sources is also shifting around because some of the easy targeting is being defended more resiliently. So they're going after things like API structures and things like that. So the attackers are shifting their behavior. And then the other side of the model of change, because you got two sides of change, you got pushback, and the other one is everybody here in the room. If you're not cleaning up your network, which you can, but as you clean up your network, you remove sources of DDoS capability, right? So doing something as simple as like taking the shadow server daily reports and going through those and cleaning up your network with public health. And those two variables will shift the model. And so that will be something to see included in future work, because this sort of modeling is really important. So I recommend people go read the paper.
Thank you. Thank you.
Hi, so I'm Azhar. I'm one of the APNIC community trainer. I really liked your presentation, and thank you for that. I just have a simple question, because we also use a lot of machine learning and AI-based models in Microsoft products also. So it says there's a lot of like false positives, and we need to train the data in order to get the accurate one. But in your experience, how much training is good enough to get the real threats, because avoid the false positive? Is there a something based on which you can say that this is the good enough and now you can get the accurate?
Yeah, so that's a super hard question. So of course we see, like if we look at number of flows, we see that it at some point converges. But you still, since it's a shift in window, we keep retraining all the time. And so in my experience, in general models that you train once and then you have a change in environment and you cannot keep applying those models. So you need to retrain all the time. So yeah, sorry.
Okay, we have one more question from the chat. Maybe you can answer this quickly in the interest of time. So from Brett O'Hara, for you black holing, do you black hole against the entire IX or on a per IX member interface basis?
No, per IX member.
All right, cool. Thank you very much. So let's give a round of applause for Christoph Pizza. Okay, introducing our second speaker. He is Roland Dobbins from NetScout Arbor. He will be speaking to us about DDoS threat landscape for 2022. Roland, are you there?
I am. Can you hear me okay?
Sorry, just 1 second. Audio in the room.
Okay.
There you go. You can proceed
Okay,
with the presentation.
Fantastic. Thank you so much. Hi, everyone. I'm Roland Dobbins. I'm a principal engineer with the ACERT team at NetScout Arbor. And in ACERT, we do a lot of different things. We discover new DDoS attack vectors. We invent new DDoS countermeasures. And we're also fourth-tier escalation for challenging, hard to mitigate DDoS attacks. We're very much hands-on practitioners. And this is kind of a sneak peek of our upcoming NetScout DDoS Threat Intelligence Report for the first half of 2022. It's not going to be released until the end of the month, but we wanted to go ahead and share some pertinent information that's specific to APAC here, especially. And the report will be available at the end of this month at netscout.com/threat report. In the meantime, you can get the previous threat report, which we presented at the previous APNIC, as a matter of fact. So here's our agenda very quickly. So we'll just go ahead and get started. So from a global perspective, the continued efforts within the operational community to get source address validation or anti-spoofing deployed to help close out some of these, the ability of miscreants to launch spoofed attacks, including reflection amplification attacks, which rely on spoofing, as Barry mentioned a few minutes ago. Those efforts continue. And so we see this great rebalancing continue away from reflection amplification attacks and towards direct path attacks. And so we take a look for the first half of the year globally, we see ACK flooding, direct path ACK flooding, number one, DDoS vector, direct path SYN flooding, number two. Then we have DNS amplification, and then we go back to some more direct path stuff stuff with RST, and then we get into TCP, reflection amplification, etc. And this gives you a little bit of another view of the same information. So ACK flooding at about 18% of the total attacks that we observed in the first half of this year, SYN flooding 17%, RST flooding and DNS amplification tied at 11%. And so if we take a look at our statistics, if we compare the last half of 2021 with the first half of this year, we can see those direct path numbers inching upwards. On the left, the blue is the second half of 2021, and then we have the first half of 2022 on the right in the green. So we can see those bars are definitely moving up towards more direct path attacks. And that includes layer 3 and layer 4 attacks, as well as layer 7 direct path attacks. And speaking of layer 7 direct path attacks, sometimes it's hard to remember that even though DNS is a key part of the internet control plane along with BGP, it is also an application. And very specifically, we see a lot of DNS direct path flooding, and almost all of those attacks are what is called DNS water torture attacks. Those are attacks where the attacker generates queries for non-existent records within a domain. There's pseudo-random label prepending attacks, also called the Mirai attack. There's dictionary-driven label substitution attack, which is sometimes called the Dyn attack. But at any rate, we can see if we take a look at the first half and the second half of 2021, we compare that to the first half of this year, 2022, we're seeing a pretty significant global uptick in those attacks. In most cases, they are reflected through abusable DNS reflectors and amplifiers. And so then we kind of see our timeline here with some spikes in mid-April, especially. And speaking of reflectors and amplifiers, if we take a look at the actually currently abused reflectors and amplifiers out there on the internet, we're seeing about 4.1 million SIT reflector amplifiers, 2.5 million NTP, 2.2 million TFTP, and so on and so forth. DNS amplification as an attack vector has dropped in popularity, and also the number of abusable DNS reflectors and amplifiers has dropped significantly as well. And this is very good. This is indicative of cleanup on the part of ISPs, because the vast majority of DNS reflectors amplifiers are actually home CPE type routers that have DNS forwarders, which are unfortunately enabled by default on the public interface. So kudos to broadband operators around the world for helping to clean up that problem. And in terms of reflection amplification vectors, I think we discovered something like 6 or 7 new vectors last year. This year, we've only had one really major new UDP reflection amplification vector that we discovered, and this was called the TP240 reflection amplification vector that was leveraging a particular brand and a set of models of some mainly enterprise-focused VoIP gear. And we at NetScout worked in conjunction with Akamai and Shadow Server and with Team Cumbria and a lot of other organizations focused on the DDoS attack space to identify how this reflection amplification vector worked, figured out how to mitigate it, and then worked with the manufacturer to help get these cleaned up. And this particular attack has the largest amplification ratio ever observed, almost 4.3 billion with a B to 1. And we saw the initial discoverers checking it out in January of this year. Then we saw automation kick in and weaponization in February. And then we saw the peak number of attacks in March. And then you see a drop off here because a lot of the remediation efforts by the vendor in conjunction with the operational community has helped clean a lot of these up. There's still some of these reflectors amplifiers out there, but not as many as there were. And you can go to the URI below to read about that, or you can also just type in like ACERT and DDoS and TP240, and it'll take you there. And it also has links to all the other folks who helped analyze this vector as well. So if we take a look at how we compare an APAC on a global basis in terms of overall DDoS attack numbers, you can see that we're in second place. Not a competition we want to win, but EMEA are leading for obvious reasons, and we do have some pretty interesting spikes, especially see one right there in March. Here in APAC, we'll talk about in a bit. Latin America at the bottom, North America below APAC in terms of daily DDoS attack numbers. So talking about APAC in particular, in the first half of this year, we observed 1.355 million DDoS attacks, striking targets here in APAC. That's about a 9% decrease overall from the second half of last year. But to put that in perspective, that's 8,600 DDoS attacks a day, or a new DDoS attack about every 10 seconds or so. The largest attack in terms of bandwidth that we observed in APAC was 672 gigabit per second attack against a wireline and wireless operator in Australia. And this was mainly a direct path attack with a lot of large packet direct path UDP flooding, as well as some other direct path vectors. In terms of throughput, the highest throughput attack that we saw was about 225 million packets per second that took place in April with small packet sizes. And most of that was SYN flooding and RST flooding, and again, some small packet UDP flooding. And that was actually directed towards the Singapore presence of a regional powerhouse in terms of cloud computing and VPS and so forth. And we believe it was intended to attack some of their customers. It lasted for about 10 minutes. And our attack durations across the board went up as well. In particular, in the 5 to 15 minute bracket, we saw a 40% increase in attacks in that duration bracket. And so that's a little bit counterintuitively, because the trend has globally been to see shorter attacks because of the prevalence of the DDoS for hire services, who offer in many cases a free tier, and they allow 5-minute attack increments, essentially, whether they're selling the service to criminal customers or whether they're people are taking advantage of the free tier of a lot of those services. But for some reason, attack durations did seem to go up here in Asia. And then if we take a look at our top vectors, the blue is second half of last year, the green is first half of this year. And so SYN flooding is actually the top vector here in APAC. So ACK flooding is at second place. It's contrary to the global trend. RST flooding about the same, fair amount of TCP reflection amplification, and DNS is down a bit, and SSDP is up a bit as well as stun. So we have some variations from the global trend in this region, but for the most part, we're pretty much following the global trends. And so if we zoom in here and take a look, in particular, we're looking at DDoS attacks, the frequency of DDoS attacks per day over the first 6 months of this year. And we can see that we have a fair amount of variation between some of these different polities. And again, that big spike in late March in particular, we'll talk about in just a minute. And if we look at the top verticals that were targeted here in APAC, per usual, wired wired broadband and transit operators, of course, led the pack. And then we also see a surge in attacks against VPS and colo and infrastructure as a service providers as well, along with supply chain folks. So that's electronic components and computer component manufacturing and distribution as well. Also saw an uptick in attacks, as well as online press sites and content sites and things of that nature. So the ROK was the most frequently attacked polity in the region in the first half of this year. More than a quarter of all DDoS attacks that we observed in APAC were targeting South Korea. Mostly broadband access operators were the targets. Most of the attacks that we saw seemed to fit the profile of what is typically associated with online gaming-inspired attacks. And of course, those attacks predominantly target wireless and wireline broadband operators. And the largest single attack that we saw targeting an operator in South Korea was a 320 gigabit per second direct path attack. And interestingly enough, these were large packets. So these weren't the typical small SYN and ACK packets that we see, but they were padded. We've seen a lot more of that since Fast Open has become more commonly deployed, and we believe that the attackers are taking advantage of the heavy SYNs that you typically see with Fast Open to try and smuggle more attack bandwidth through to get it on target. And of course, in some cases, the throughput is actually more important than bandwidth, so that can be counterproductive. Second most attacked polity in the region was India, with 16% of all DDoS attacks in the region targeting India in the first half of this year. Their highest bandwidth attack was a 519 gigabit per second multi-vector reflection amplification attack. And the highest throughput attack, 212 million packets per second, which was an ACK flood and a DNS water torture attack with a little bit of NTP and DNS reflection amplification thrown in. And there were some significant variations in DDoS attack cadence against India over the first half of this year, and they seem to bear some relationship to India's diplomatic stance vis-a-vis the Russia-Ukraine conflict, as well as in the run-up to the recent presidential election being held in India. And so if we take a look here at the attacks targeting India and Taiwan, and we also threw in Belize and Latin America by way of comparison, if we take a look here, we look in mid-February and we see this dotted line. What does this line represent? This is the date of the onset of the Russia-Ukraine conflict. And we can see that in the run-up to that, in India especially, we saw a gradual rise of attacks, we saw some dips and then some immediate spikes right after the initiation of hostilities there. And then that carried over a bit, started to decline, and then started to rise briefly towards the end of June. And there's that spike again, and I promise you we'll get to that spike shortly. So Hong Kong was the third most frequently attacked polity in the region, 15% of all DDoS attacks. Highest bandwidth attack was another multi-vector 550 gigabit per second attack, and the highest throughput attack was 220 million packets per second, mostly small packet SYN, ACK, and RST flooding with a little bit of SSDP reflection amplification. The cadence of attacks were largely consistent in Hong Kong across the first half of the year. There was, however, a measurable spike that seemed to coincide with the regional Shangri-La security dialogue in early June, which was held in Singapore, actually. China, fourth most attacked, 11% of all DDoS attacks in the region targeting China. A lot of variations here in DDoS attack cadence as well, and they seem to coincide extremely closely with rising and falling levels of diplomatic tensions in the region and internationally. The most of the organizations targeted in China appear to be cloud computing, VPS, hosting, colo infrastructure as a service, along with the typical broadband operators and online electronics retailers and distributors. And in particular, with almost all the attacks that we saw against the cloud computing and VPS and hosting and colos, those attacks did not seem to be targeting those organizations on their own stick, but rather prominent customers of theirs were being targeted from time to time. And then we have Singapore, the fifth most frequently attacked polity in the region, with 8.6% of all DDoS attacks in APAC targeting Singapore during the first half of the year. There were some variation in attack cadence targeting Singapore, but nothing that really seemed to correspond with any regional or international external events. And so here's the bonus, Taiwan. And so you remember that spike that we saw in late March? Taiwan only received about 6% of the DDoS attacks in the region in the first half of this year, but they had the single largest day of DDoS in terms of attack counts in one day. That was almost 3,600 DDoS attacks in a single day in late March targeting Taiwan. And that spike in attacks appeared to coincide with some public pronouncements from representatives of Taiwan, again, regarding the Russia-Ukraine conflict. And interestingly enough, most of this was direct path attacks, and a lot of the IP addresses that were involved in this particular attack campaign, this one-day attack campaign, appear to be cited in Russia, for what it's worth. And so then you can see this quite clearly. And if we take a look here at China and Hong Kong, we can see some pretty significant dips and spikes. And that's what I was referring to earlier in terms of the ebb and flow of attacks that in many cases seem to be related to regional and international external events. And now we see very clearly that bright blue spike of attacks against Taiwan in late March. So in the industry, what are we taking a look at in terms of new ways to help deal with DDoS attacks? We're really taking a look at something that we call Ddos suppression. So we're moving here in Asia towards ubiquitous deployment of 5G. And from the wireline perspective, gig to the premise internet is very, very common. And what this means is that we're seeing orders of magnitude more bandwidth available for each particular node, and a whole lot more nodes, especially on the 5G side. And a lot of them are IoT devices that are not coded securely. They're insecure and largely unsecurable. And a lot of them are actually using layer 7 protocols to communicate with whatever they need to talk to in terms of their machine-to-machine communications, protocols that don't suit themselves towards being cited behind a CGNAT. And of course, with V6, we don't have CGNAT anyway. And so what does this mean? This means that we're getting more and more populations of vulnerable devices that can relatively easily be botted and converted into DDoS-capable botnets. And that means a potential flood of traffic that can seriously disrupt operator networks. And what we can't do is stand back and say, okay, well, we're going to wait until we see all this outbound and crossbound DDoS attack traffic converge topologically within our network, because then we have a very, very big problem. And we may have issues with core bandwidth and certainly bandwidth out to the aggregation edge as well. And so what we really need to do is to say, okay, we've been focusing on DDoS mitigation. Now let's take a look at DDoS suppression, and let's take the same kinds of technologies that we've been using, network infrastructure-based techniques like FlowSpec and SRTBH and DRTBH, as well as intelligent DDoS mitigation. And we've been dealing with inbound attacks mainly coming across our peering links. We now need to really focus on the outbound attacks and the crossbound attacks where customer A has devices that are attacking customer B. And we need to actually stop that DDoS attack traffic as close to that customer aggregation edge as possible. And so that's what we really need to move towards. And that's what we're calling DDoS suppression. Yeah, go ahead.
If you can please try to finish up in 2 minutes. Thank you.
Yep, absolutely. This is our DDoS suppression model. As you can see, we have mitigation up there for inbound attacks, and then outbound and crossbound are what we're calling DDoS suppression. So what are our conclusions? The direct path DDoS attacks continue to increase, but reflection amplification hasn't gone away. It's getting rarer, but it's still unfortunately pretty commonplace. Most of the DDoS attack trends here in APAC are in line with global trends. We see very, very strong correlations between major DDoS attack campaigns and attacks and various regional and global tensions in terms of external factors. And as we get more and more 5G and get to the home, get to the premise deployed here in APAC, we really need to start moving towards a default stance, not just of DDoS mitigation, but DDoS suppression. And you can get the threat report at netscout.com/threat report completely free. The full threat report will be released at the end of this month. And that's all I had. So thank you very much.
Awesome. Thank you, Roland. We can entertain 1 or 2 quick questions if there is any. If not, then yes, quick one, please.
Hi, Roland, can you hear me?
Yes, I can.
Okay, I wanted to ask you about one of your slides where you talked about the attacks in Hong Kong. And you, in your last bullet point, you mentioned something about the peak coinciding with the end of the Shangri-La dialogue. I just wanted to understand a bit better, how did you correlate the two? Because they're in 2 different countries. And you know,
yes.
What made you come to that conclusion? What were the key indicators?
We're not claiming causation. We are stating correlation. The correlation is because there were public statements that were released as part of the Shangri-La dialogue, and then immediately the attacks kicked in. It could be a coincidence, but this spike in attacks stood out from a statistical standpoint as well as in terms of the targets. And so we're not claiming causation here. It was very hard to actually truly attribute DDoS attacks, but what we are saying is across the entire region in the first half of this year, we saw some very strong apparent correlations between various external events regionally and internationally. And in particular, this one stood out for us in Hong Kong. It could be coincidence, we don't know, but it looked pretty potentially related to us, which is why we actually wanted to go ahead and highlight it here. Hope that makes sense.
Thanks. And is there description of this in your report that you said will be released at the end of this month?
We talk a little bit more about it. We don't necessarily get into a lot of the details of that sort of thing in the report itself. But if you have further questions, you can send me email, roland.dobbins@netscout.com, and we can discuss it further. Okay?
Okay, thank you, Roland.
Awesome.
Thank you all very
Roland.
much. Good question. Thank you. Yep.
Another round of applause for Roland, please. Okay, down to our final speaker for today. We have Ben Lam from NTT Australia, who will be sharing how to identify routing security flaws and how to fix it.
Good afternoon, everyone. This is Ben Lam here from NTT Australia. I'm heading the network engineering operations and have been in industrial about 20 years, more than 20 years, and have been seeing a lot of routing security flaws happening here and there. So today I would like to talk about identify routing security flaws and how to fix it together. Before I start, please let me put a disclaimer on. Any views or opinions presented in this presentation are my personal and do not express any views or opinions of my employer. Any views or opinions come from my personal experience, and I would like to share to raise awareness and are not to intend to malign any individual company or organization. So let me start my presentation today. If you have seen many attacks happening in the past, targeting our operator infrastructure, we are living in a connected world. Everything happened on the internet is related to one another. And recently, you don't see much on the news. Is that our security routing table is secure enough that you don't see any route leak or route hijack published on the news anymore? In fact, we have seen that every day. And that is the reason why I'm here today and want to raise some awareness and hope that we can work together and fix those flaws that exist in today's routing security. This is today's topic. I would like to focus on log transit leaks. What it means, we are going to go into detail later. ROA, RPKI validation in today routing security. And also the last is BGP alerter. I would like to introduce you why those route leaks still occurred. You would ask why, because if you take a look at the eBGP relationship and the best path selection, it's very simple. As an ISP, we are sitting in the middle. We usually have customer, peer or upstream. Some of the large upstream, they're just peering each other. We call transit free, right? They exchange the routes, customer together. And the best path selection usually come from customer route first, and then peer routes and transit route, which means if anything come to our routing table as a customer route, we'll get the highest local preference. However, if there is a route leak into our routing table with the most specific route, that will win everything, right? Because it doesn't make sense where you put the high local preference for different prefix where you have the most specific route coming to the routing table. That's always the preferable path. That's the reason why we see leak occur here and there, or even route hijack take those advantages. And when you see route leak occurred, most of the time you would see is non-transit free ASN. We call it large transit, so up in the AS part, behind your customer or from the peering perspective. And reason, the challenge for us today is most of the customer leak the route through to the upstream, and then regional ISP or tier one, even tier one, accept that as a customer route. And because of that, that's very high impact to the global internet routing security. And I put down there is some major patterns that I observe over the time. It's very popular where your customer now appear to be route learned through the one upstream and leak to another. The pattern number two is most likely from the customer downstream, the further downstream, leak the upstream, and then go and get into your routing table as a customer. And because of that, you continue forward it to the upstream. The pattern three we see is a most likely the security configuration error or human error or something that can be prevented, I would say, because from the large ISP, I mean large ISP here is more a tier 1 level, a global tier 1, like a peer routes, even the entire routing table to another peer. So let's dive into the detailed case study, which is I'm going to use the actual case study because I believe that is the most important to raise awareness so that we have the most outcome from this talk. And what is missing, in fact, from those route hijack, you will see is two methods of preventing route leak: is log large transit leak. The other one is proper route tag or route filter not in place. So let's study case study number 1. If you look at the left-hand side, this is the AS7473 have a customer AS connected as a direct part, and then the route learn 1110.224.240/20 advertised as a customer route to the upstream provider. It's first detected as route leak by BGP stream just July this year, and you see in that AS part there's a large transit leak AS number sitting behind, right? Why it's happened like this? This is just my assumption. I strongly believe so. Is it could be a customer link outage, or it could be a customer change the announcement, or whichever way. And then because 7470 still have a next referable route to that destination became active, right? Because usually when you're looking at routing table, you have multi-part customer route referable first, and then peer route or one work stream via the other. And then because of the current outbound route filters only based on customer prefixes, and because it's much of outbound route filter, that route was linked to another upstream provider. So that is one of the cases that we see. The second case that here you see also on the left-hand side, in the normal situation where the downstream customer have a normal part, you don't see any known transit free showing up in this AS part, and it's normal. One day, the leak occurred, right? And then that leak was detected where you see now the route leak AS part have even 2 large transit provider inserted in the AS part. Why it happened again? Right, so that's my assumption again. There should have some way happening between the direct part and the downstream customer. In this case, I'm playing as a ISP 7473, seeing 134.078 leak the route from one upstream to the customer link. And because of customer link, even though you learned the route from multiple parts, but because of customer, right, is you refer that and refer that, and then because of without hardening the outbound route filter, then that's continue leaking through the global internet. And then unfortunately at a tier 1 level, also accept that route leak as a customer route. So you see the impact of small flaw happen on the internet routing table is very scary. And this is plus. Actually, 2 days ago, before I finalized the presentation, I found another interesting leak. So I really want to share with you here. So let's take a look at this SLAT 22. It's normal part announced by one of the ISP in Taiwan, 9505, announced to IX 4635, you know, it's HKIX. And then route leaks detected. This time, it's very interesting. A subnet SLAT 19 leaked through that ISP with a downstream customer 9924. And why is happened? From the analysis, I could see 7533, in fact, doing unequal prefix length announcement for some reason, and one going to 9505 is SLAT 24 more specific, that is normal part, while the subnet SLAT 19 leaked to 3491, as well as you see 9924, learn that from transit provider 3491, and then leak through 9505. So AS 9505 starting to leak through, tier 1 and IX, and because all of the simple relationship, customer, peer, and transit, and that become a route leak. A very, very basic customer relationship. You adjusted too much, and that route come in somehow, look into the routing table, and that you believe that is still valid customer route path, and then continue forward to the routing table. So more and more, if you have a time, I would like you to take those case and study by yourself and learn what is missing in those ISP as we speak. So that is a small leak that you occur. It's only 1 or 2 refixes happen here and there. And actually this year, so in March, the BGP stream detected continuous leak from one tier 1 provider, leak and visible 300 routes visible. If you think about a global tier 1, they would have a lot of direct customer route or different path, but visible 300 routes like demonstrate something went wrong on that day, and it's very long hours of route leak and tie another tier 1 SP to another tier 1. And I put that link there so you can look into that later. What is missing on those leak? I mentioned earlier, reject large transit AS coming in from customer and before going out to upstream. So you know you are the one who turn on the BGP setting or configuration with the customer. You know that is a customer link or peer or transit. We need to have a proper policy in place beyond just a prefix filter update. Because most of us, you know, in our legacy way, we're using the route object to filter, and then that is where we see is missing in today the route leak. So recheck when you imported the route and even the export when it's not just filters out, right? Another very effective, and I think it's very, like I say, simple and effective is when you enable the peer and route learn through that peer, we need to really set on the tag, right? So if you properly design your routing security and configurations, this is the first thing you need to do when we accept the routes. Tag customer, tag peer, tag transit. And then I put down there is a matrix of route filter. You can, based on that, and filter out. If somehow the customer route is disappear, the next available route, even though it's match the prefix filter to allow to send outbound to upstream, but because of this, you have this route tag in place. You could identify another second chance to identify, no, this is peer route or this is a transit route. I should not send out to another transit provider, right? So that is very effective solution, I would say, and I would like to introduce you. That is route leak, but why route hijack still so successful? Everyone, we're trying to protect a lot about our, you know, direct attack, right? DDoS or security from the premise. We protect ourselves. How about the transit part? And what today bring us to still the route hijack so successful is IP address resource holder delay in signing ROA. Another one is transit provider also not implementing API validation. It has been years. I remember I presented this topic in 2019 in Thailand at the time, APNIC 48, and I talk about the same subject, that missing all of those is a very high risk for the route hijack occurred. Why we say the ROA is so important? Because when you're looking at route object today, it's very old kind of mechanism where we validate the routes, because no longer just everyone can really, if you have a membership, you can create any route object, right, without further verification. And the route objects is only 2 attributes to compare, to validate. That is prefix length and AS origin. What brings up today is ROA is much more secure, because it's have a max length attribute added on, as well as it's only IP resource holder can really assign or, you know, route objects and declare you own the authorization to announce to the global routing table. And because of that, you help the service provider like us or operator who has API validation can have the way to verify whether the route is valid or not. That is very important. As today, when you're looking at global routing table. If you are an engineer, you can jump to the routing, your router, and you can do some so route. You would easily tell whether this AS announce those prefixes did register, ROA or not, or just not register ROA. And some insecure ISP, whether you have route object ROA, they don't have a mean to verify, right? Because they haven't implemented API validation. So that happened. Majority still today. I see a lot of regional ISP is not implementing this yet. Another part of today global internet is lucky enough there's a lot of tier 1 now adopting API validation. Would that help a lot? Where route object coming in, ROA, majority ROA will certainly see whether it's valid or invalid. Then the operator ISP can take further action by doing filter, drop the invalid route object. On this left-hand side, you see route object itself without ROA is a non-status. Even our tier 1, service provider have API validation. We cannot really identify you valid or not. Let's take a look at case study. So I'll give you more information about why it's so important. So this is one of the route hijack case with the ROA size. So Amazon have the slack 15 here. I put on the slide. Announced by 16509 with the valid route objects defined. One day, it's were hijacked by AS. One of the AS leaked slack 24 more specific into the routing table. And because some of the insecure ISP without API validation, they could not identify that is actually route hijack, right? Somehow it's leaked into the routing table, and then it's accepted at the very large service provider. On the other side, lucky enough, majority ISP who has API-based validation could tell slack 24 is invalid, and they reject it. So this is that actually helped and to stop the hijack to spread globally. So with the ROA side, in another case, if you see here is invalid ROA setting. So the IP address owner happened to be in Australia, unfortunately, and they are now slack 13 as a subnet also have ROA with the max length only 13. When that comes, when you see the routing active in routing table is valid, that's cool. But one day there was a slack 16 inserted into the routing table. And because even though you protected the subnet and that IP is clearly belong to you, but there's no ROA or sign yet, or maybe misset or whatever, right? Not enabled for that, but to cover the whole length of your entire IP address holder resources. And because of that, it's hijacked globally. Why? Because both insecure or secure ISP could not identify whether that is valid or not valid, right? And then if you see the AS that I saw, AS path when I saw the route of slash 16, that is the day actually it's where hijack. I was on the routing table, and I see clearly even 1221 the upstream accepted that route hijack too. So you see the amplifier of without enabling the ROA to protect your IP resources. That is scary in today, global internet secure world. So, and I most likely guess if the victim AS doesn't have a proper route filter, they might also accept that route hijack too. So now the question is now for you. Have you signed your ROA yet?
Can you please to finish up in 2 minutes, please? Thank you.
Yeah, thank you very much. You has a status here is still a lot. It's not signed ROA. And in here you see even FAN. There's one very known AS there is not signing the ROA. And CDN cloud provider, look at that. There's a lot of unknown. A lot of people argue that I could announce more specific, and that is not enough. As announced slack 24, I don't worry about a more specific route hijack anymore. That is very misconception, because you know, remember the routing relationship, EBGP from customer, transit part, right? So if once it's linked as a customer route, it's always become an active. So sign your ROA to protect your resources. And how about to detect route jack in real time? I want to introduce your BGP alerter, and the GitHub link there is actually, we make it as like open source for you to use. It's very simple to enable, and you can detect and analyze when it's come to hijack your prefix. You can start analyze and understand how to fix it. So this is one of the case study that I captured from the BGP alerter. And I put down here is a checklist. You can go back and look through, make sure you have all of these filters in place. And the future of the internet is together we do right things. So go back, review your prefix filter, make sure you have those methods in place, and enable ROA APK validation. Hardening IP transits, I believe always is a small little thing makes a big difference. Thank you very much. That's the end of my presentation.
All right, thank you very much, Ben. I don't think there are questions in the room. If there is anything, maybe please reach out to any of the speakers during the break or just ping them over Zoom. Thank you very much for attending technical session 2. We will be back in about 15 minutes for the next session. Thank you.
What we doing? To the whole block. Yo, what you got there? Oh, did you not hear? And he's taking the whole shop. Yeah, her she wanna know me better, but I'm on the top 10. Gotta match my energy. You see, I'm in the top. Yeah, it's top 10. Hey.
I can feel it in my bones, and nothing to ask more. Got me looking like a clown. Tell me why we slide it down. Tell me I'll be what I eat.
If the speakers for session 3 are in the room, can they come and see me, please?
I can tell you're a dancer, throwing your hands in the air that you answer. When I ask you if you want me, you're a panther. I'm a little too for a boy, you a trans girl. I put on left, right, it just says cancer. I can go change if you want to. I mean no things that you don't do. I won't put a foot on the floor unless I am sure. You just jump head first, hope for an encore. Oh, look, girl. I can pay for the nice return. I can feel it in my bones.